Morning, class. How you guys doing? We're here today to talk about angular momentum. So linear momentum or translational momentum we know as p vector, which is equal to m times v. And angular momentum is similar, related to linear momentum p, but is associated with circular motion most of the time. So we're going to focus today on finding the angular momentum. Here's the symbol that we use for angular momentum. It's a vector. We use L vector. And we're going to start by finding the angular momentum of a single point mass m. Now, I know that normally when we talk about angular momentum, or rotational quantities, we tend to talk about rotating rigid bodies. So we'd have an axis of rotation and maybe some body that moves around. That axis of rotation consists of many different point particles. But the the angular momentum of a single point particle is also relevant, and we're going to use that information eventually to treat the rigid body and to find the angular momentum for a rigid body that rotates. So this right here is the equation of the angular momentum for a single point mass m, where m, here it is in the momentum portion, p, right? So it's related to the linear momentum m times v vector, but it's related via this cross product with an r vector. Now, this r vector can be the same r vector we're used to seeing, which is from the axis of rotation to where the point particle is located. Instead of where the force is, it's to where the momentum vector is, which is with the point mass. But we actually have a lot of freedom associated with this r vector. We can choose it, especially in the case where we don't have a specific axis of rotation, or there are many points along the axis of rotation that we can choose. So you're going to see there's a little bit more freedom with what this r vector can be, but it still points from some origin to the place at which the momentum is. And we're going to work through some examples. So this equation is the equation for the angular momentum of a single point mass. Later on, we're going to find the angular momentum for a rotating rigid body. And you see that takes the form of rotational mass times rotational velocity, similar to the linear momentum. So later on, we're going to be looking at this. Okay. What I want to talk about first is where this comes from. And we're going to find that just like when we talked about regular linear momentum, p, you'll remember that we rewrote Newton's second law, sum of forces equals to ma. We rewrote it as the sum of forces equals to dp dt. And in a similar way, we're going to do the same thing for torques. We're going to find the same relationship between the rotational force, which is torque, and the rotational momentum, or angular momentum, L vector. So let's get started. So we can think about the sum of torques acting on a system as, the sum of all of the individual torques acting on a system. And if our system is a point mass, right, this is just describing all of the forces acting on our point mass with respect to our axis of rotation, so that our vector would be the same. So maybe here's a point mass m, and maybe here's the axis of rotation, and maybe this is like force 1, force 2, force 3, etc. Well, the r vector would point from the axis of rotation to where the forces are acting, and it's going to be the same for a point mass because all of the forces act on the point mass. It takes up no volume, so they're all going to have the same r vector when I go through and sum all the torques for a point mass. And so this would just be the addition of all of the torques, one for each force that acts. Well, I can rewrite this since the r is the same as the sum of forces in the cross product. So r cross the sum of forces. It's a little bit easier notation. And also I have this relationship here for Newton's second law in terms of momentum, which means I can rewrite the sum of torques equal to r cross dp dt. So what I'm going to say is that this is in fact equal to the time derivative of r cross p. Now, that's not obvious, so let me prove this to you. And I'm going to do that by looking at just the time derivative of r cross p. And using chain rule, I'm going to act with the derivative first on the first vector, and then second on the second vector. And I'm going to notice that this is how the r vector changes with time. Of course, another name for that is the velocity. And I'm going to go ahead and rewrite the right-hand side here as v cross. And just to make a point, I'm going to rewrite p. We know that it's m times v. I'm going to rewrite p in here. And I'm going to leave this second term alone, because actually that's what I'm trying to prove. And then what we have is v crossed with m times v. Well, this whole thing can be, the m can be just taken right out of there because it's a constant. And this is the cross product of a vector with itself. So remember, for a cross product to be zero, the vectors have to be parallel. And these are the same vectors, so they're literally parallel to themselves. Therefore, this whole thing is zero, or the null vector. So in general, that means that this whole term right here is zero. And in fact, we do have this identity proven. And so you'll notice that what that means is that the sum of torques is equal to the time derivative of r cross p. Well, r cross p is how we're defining the angular momentum of a single point mass. So really, at this point, we're defining the angular momentum of a point mass right now. Now this is also equal to I times alpha. And of course, we're going to be talking about angular momentum in cases where this is zero and not zero, very similar to what we did with regular momentum, but not for a little while first. Here I'm just justifying to you that we also have this relationship between angular momentum and torque the same way we did with linear momentum and forces. And we're going to be exploring this relationship moving forward, as well as kind of dealing with this R cross P. So as a reminder for the cross product, I kind of have it written here, and we're going to be referring to this, and maybe it's been a while since you've looked at the cross product. I'm going to be using the determinant form of this, which is effectively the same thing, right? Which would look like x hat, y hat, z hat, ax, ay, az, bx, by, bz. So if you see me writing this, it's the same as this right here. And you can just choose to use this formula instead. Okay. So, let's start by finding the angular momentum of a moving particle. Now, I always find this problem a little bit weird because, let me kind of zoom in on this. What I have here is a mass m, and it's moving here along the positive x hat axis with some velocity v. That also means that it has a momentum p is also in this direction, right? Pointing this way, m times v. Now, this motion is purely linear, right? This is just moving in one dimension. There's no rotation associated with it. And we're talking about angular momentum. So to me, this problem is a little bit weird. How does a point particle moving in purely linear motion have angular momentum? And the answer is that it can, but it also doesn't have to. And that's because it's not really moving in a circle, but it still has an angular momentum associated with it if you choose the right origin. But you can always find an origin in this case where the angular momentum is in fact zero. And I'll show you what I mean. So let's consider this a warm-up exercise for finding angular momentum. And I'm also going to be just saying that this point mass is also feeling a force. It's a constant force, so I'm going to call it F naught in the x hat that drives it along the x-axis. So v is not a constant. I'm going to argue that it changes with time. And, in fact, if I had to find the acceleration of the system, it would just be F naught over m in the x hat, assuming that no other forces are acting on this, no net forces. So there could be a force in the y hat, like the normal force, and then of course gravity could be acting on it, but I'm going to assume that those sum up to be zero. And so the net force is just this one. Therefore I have acceleration. Okay. And what I've done here is I've kind of automatically chosen an origin. So here, right, is the location of an origin that has been defined for me just already in this problem. So if I was going to go calculating the angular momentum of this particle, I would assume that this is the origin for my r vector. It's not really an axis of rotation, right, because this thing isn't rotating. So it's more of a chosen origin with a position vector. And I can right away just go ahead and find the angular momentum. Now, I know in advance, because I remember and use the cross product frequently, that only the perpendicular components are going to survive. And what that means for me is that if I break up this r vector into components along the positive z hat and along the positive x hat, right? So this plus this will equal my r vector. I know that this is the only component that's going to survive because this one is perpendicular to this, and that the parallel component of the vector will not survive. That's just the nature of the cross product itself. It picks out perpendicular components and multiplies it. But we can be specific. This, if this angle here is theta, then this angle here is theta. And I can write out the whole r vector. It's going to have a sine theta component. Well, actually, I just was calling that d. Funny of me. Maybe I should erase that. Let's get rid of that. Instead, we'll just say that we know the magnitude of the r vector here. Oops. And although that d is important because it really is the only component that's going to contribute, I'm going to say that since I started this way, I'm going to go the other way. So in the positive z hat component, in the positive z hat direction, I have an r sine theta component. That's the sine theta component. And in the positive x hat direction, I have the cosine theta component. And so I can represent my r vector like this. Similarly, I can represent the p vector as just m times v. And it's purely moving in the x hat direction. And so if I wanted to look at L equal to R cross P, I would actually use the determinant. You guys can use the formula that I had on the previous page. But here's my determinant. For the first vector R, I have an x hat and a z hat, but no y hat component. So write out my vector. And for the second vector, I only have an x hat component. And performing this, I don't know if you guys do the same thing I do. Cross that one out. This times this is 0 in the x hat. This one, this times this is not 0 in the y hat, so I have a y hat component. Minus y hat minus r sine theta times mv. And in the z hat, I'll have 0 components. So taking the cross product, you should find that this equals positive r mv sine of theta in the y hat direction. So my resultant vector, the actual angular momentum vector associated with this particle, actually points in the positive y hat direction, perpendicular to r and mv. Also, this r sine theta, I told you that it was just going to be picking out the perpendicular component, and you can really see that right now, right? This is r sine theta times mv in the y hat, and that's what I had denoted this distance of d before. That's just this. So in fact, it's really just picking out the perpendicular component d of the r vector and multiplying that by m times v, and all of that in the perpendicular direction. Now, you could have used the right-hand rule that I taught you to kind of figure out this direction. There's even a better right-hand rule to use, which is this. If you take your pinky of your right hand, so imagine a hand, right? So I'm going to draw a right hand, I guess. Good luck to me. All right, so this is your right hand. And here's your pinky, believe it or not, and here's your thumb. And your hand actually is going to be able to fold. So this is your right hand. In this configuration, it could only fold these fingers by moving them out of the page right now, or out of the board, right? So if you take your right hand, you'll see what I mean. Those can only fold towards you if you put your thumb up and hold your fingers in that position. So what we do is we align our pinky along the first vector. That's our r vector. and we align it in such a way that we could cross our fingers in the direction of the second vector. So if I took my hand, oh my gosh, this is so hard. Let me try this. If I took my hand, my pinky, so my thumb would be, oh my gosh. I don't know if I can do this. All right, my pinky would be aligned here. And it would be I would align my pinky in such a way I could fold my fingers towards the second vector. Now, I know that not all of it is exactly perpendicular, but in such a way that I can do this. And the only way for that to occur is if my thumb is pointing upwards like this. Oh my gosh. So the only way I can line my pinkies up like this and cross my fingers towards P is if my thumb is pointing up along the positive y-hat direction. Don't know if I'm explaining this really well, but it's the second right-hand rule that really works for cross products like this. Or you can just take the cross product, write things out. Okay, sorry if I butchered that. I tried. Okay, so anyhow, what we found is the angular momentum of this particle. And so it has it, and again, I find this a little bit weird because this is a particle moving in just straight, regular, linear motion, but that's okay. I also can spend some time verifying that dl dt is equal to the sum of torques here. And so there is a torque that's going to be acting on my system because I have a force. Because I have a force, I have an acceleration, which we discussed here. And because I have an acceleration, that means this v is changing as a function of time. In fact, if I had to write v, I would say it's a times t in the x-hat, because this is a constant acceleration. So it would look something like f naught over m times t in the x-hat plus whatever initial velocity, which I suppose for simplicity, I'm just going to go ahead and zero out right now. And then my position vector would be very simply 1/2 a t squared in the x-hat plus whatever initial position, which I'm just going to zero out for simplicity. And I could, of course, plug in my position vector, or my acceleration here, f naught over m times t squared in the x-hat. And so you can see my position really only changes in the x direction as a function of time. So really I should just say that this has some x of t, 1/2 f naught over m times t squared. And x as a function of time would be then just this here on the graph, this distance, and it would be changing as a function of time. And my velocity also would be changing as a function of time. So if I had to rewrite, my speed, or if I had to rewrite my angular momentum vector, I would be rewriting it in terms of a function of time right now. And that's related to my force. And for my angular momentum vector, I'll rewrite it over here. I have r sine theta m times v, and v I'm going to rewrite as f naught over m times t, and all of this in the positive y-hat direction. And this simplifies a little bit, right? I can then write L is equal to r sine theta. The m's will cancel, f naught times t in the y-hat. So I do see that there is a time dependence here on my angular momentum, which is telling me that as time moves on, the angular momentum is actually increasing as a function of time as I move along the x-axis. So it's not constant, it's sitting there and it's increasing as it moves along. It also tells me, though, that there is a net torque acting on the system because the time rate of change of the angular momentum vector is related to the net torque. So let's just go ahead and prove that really quickly. And the way that we're going to do that is I'm going to look at the time rate of change of the angular momentum vector. The only thing that's changing, because remember the y hat is constant, under the derivative is this time. And of course the time to the 1th power, the first derivative is 1. And so dl dt is not 0. In fact, it is r sine theta f naught in the y hat. And so I've taken the time derivative, and what I'm going to do now is check this and say, is this also equal to the sum of torques acting on my system? So let's kind of just quickly redraw this. So here I have M, and here is the force that's acting on it. It's exclusively in the x hat direction. And I have to be careful because when I'm talking about the change in angular momentum and the torque, I have to make sure I'm using the same axes. I don't have any other axes that I've talked about yet, but I would have to make sure that for the torque, I'm using the same axes that I used to find the angular momentum. So here's going to be my axis, and this will also be my r vector again. It's the same r vector as before. It points from the axis of rotation, which here is loosely chosen because there's no actual rotation, to where the force is acting. And so the net torque would then be r cross f, right? I know my r vector already is equal to r cosine theta x hat plus r sine theta z hat. And my f vector is equal to f naught in the x hat. And I could take the determinant. I could also use the right-hand rule, just so you guys know, to determine the direction of this thing. Line my pinky in this along this vector in such a way I can bend it towards this one, and my thumb should be pointing in the minus. Oops. And my thumb, oops, I can't draw it, but my thumb should be pointing in this direction right here, positive y hat. But if I can't figure that out because it's hard to do this on the page, maybe I'll make you guys a video for the other right-hand rule in a little bit. I can always take the determinant of r cross f and when you do that, 0, not 0, 0, there's only a y hat component that lives. Or r cross f is equal to positive r sine theta f naught in the positive y hat. So there's only one force acting on my mass, and so that's the net torque acting on the system. And I see it as exactly the same as the time derivative of the angular momentum, where I've been careful to make sure I'm keeping the same origin on these things. Okay. So we're just kind of playing around here. And what I'm going to do now for my next trick is to just move the origin from here to here and to do a similar analysis. I'm moving it here because this, if I move the origin here for my r vector, I'm not going to change the origin of the whole axes that I have defined here. I'm just going to move what I'm calling the origin. And I'm going to show you that that really we can find angular momentum 0 with just a different origin choice. I guess I can move the whole direction of the origin, but so let's all right, let's look at this again. So what I'm going to do is, okay, I'll just shift the whole origin here. Here it is. So maybe instead of an axis that I had before, I would just now be looking like this. Okay, that looks better. So, yeah. Let's look at the angular momentum now with this new choice of origin. Not much has changed in the x-hat, except for it's shifted over a little bit. But if I wrote v out, it would still be v in the x-hat. Or if I kind of kept true to my constant force that was acting on it, I would rewrite v as a function of time. It's really my r vector that's changed here, and in fact, r is now entirely in the x-hat direction. Here it is, it's pointing from the new axes that I've chosen. And of course, I can choose it anywhere I want to because this thing actually isn't rotating, right? So from here to here, the magnitude of that r vector is just going to be r. So I should get rid of this, all of this right here. I guess it's a little confusing, but the magnitude is r. And actually r, this distance r, whoops, this distance of r right here is actually what I was calling x before. It's 1/2 at squared. It's actually a function of time too, and if I was being technical, I would write it like this. And when I go to take the cross product of angular momentum, right, I'm really just going to be taking the cross product of two vectors that are both entirely in the x-hat direction. So regardless of this dependence on time right here, I'm still looking at x-hat crossed with x-hat. Those vectors are parallel to one another. Here's r and here's mv. The cross product of two perpendicular vectors, and you can prove it to yourself, of course, is just, or two parallel vectors, of course, is just 0. So the angular momentum can be 0. And all that I did was to change the axes from here to here. So this is likely the case because this is not exhibiting any circular motion. So it's true I can find an axis where it's 0 or not 0. So by analogy to what we've done before, this also means that since the sum of, since the sum of torques is equal to dl dt, of course, that's still 0 because the time derivative of something 0 is 0. That also means my sum of torques should be 0 with respect to that axis. And of course, it's the same argument as before because there's only one force acting on it. This force is acting entirely in the x-hat direction, and the r vector is also entirely some stuff in the x-hat direction. So the cross product between those two is also 0. Right? Here's the r vector, here's the force. They're parallel, therefore 0. So we can also see just by looking at the torques that that's also 0 too. Okay, I know this has been a little long, but we're going to kind of continue on this vein, maybe with a little bit of a harder problem of something that's actually moving in a circle. So I'm going to have it moving in this circle in the horizontal plane. So in fact, this is the conical pendulum that we've seen before. This is the positive y-hat direction, and I can call this the positive x-hat direction, which means the positive z-hat direction is out of the board. And right now, as this is the conical pendulum problem, if you remember, this is just moving in the, it's just a circle in the xz plane. So if I looked down from the top, so if I was at point N, looking down, so this is like a top view, I would be looking at something in the xz plane right now. And right now, if this is my mass m on this side over here, it's going to be moving with a tangential velocity out of the board. And so it's moving here, it's moving around like this, just in the XZ plane. And that also means that when it's over here, I'm going to say that it's moving with it's actually going to be a constant tangential velocity into the board. So right now, the velocity vector is out of the board tangentially, and if the mass is over here, right, it's going to be into the board. Into the board, that's the minus c hat direction. But it is moving tangentially, right? At different points, it's tangential as it moves around that circle. And here is the center of my circle, right here at point M, right? Here's the center of the circle. And this is the radius. This is the radius. And you can prove to yourself that's L sine theta. And if you remember the conical pendulum problem before, this is something that we had to do. In fact, the conical pendulum, we used circular motion to say, to solve this thing for V. The sum of forces in the y equals 0, and the sum of forces radial are mv squared over r. And doing a quick force body analysis, just to remind you guys of the problem, I had tension and gravity were the two forces acting on the system. The force that points radially inward is a component of the tension force. And this angle theta right here is fixed. So theta is a constant for this whole problem. And it remains fixed and traces out a conical pendulum. It's as a conic shape as it moves around in a circle because theta is fixed. Anyhow, and I can break up this tension into a component t sine theta radially inward and a component just in the positive y hat. And so the sum of forces radially inward are just t sine theta, and the sum of forces in the y were just t cosine theta minus mg equals to 0. When I also plug in that r is L sine theta, the radius, I can solve V to be the square root of L g sine theta times tangent theta. And I'm quickly writing this up here to remind you. But you solve these three, you get this, and this is the magnitude of this tangential velocity vector as it moves along. It's a constant, because theta is a constant, and length and g are a constant too. It's constant because there's no tangentially pointing forces. Yeah, this is I think we solved this problem in the homework, actually, as a homework problem. Okay, so this is the conical pendulum, but now we're going to be approaching it from an angular momentum point of view. And this is specifically the angular momentum of a point particle because I have a point particle. And this one is now tracing out a circle, so we're going to be hard pressed to find an axis or an origin, how I define my r vector, such that this is 0. And in fact, the only one is if you define your origin to be on this thing as it rotates around, then you'll be able to. So in fact, there's really no other way to, except for by shifting your frame of reference to find an L equals to 0 frame. But that really has to do with the fact that it's actually rotating now. So when we talk about L equals to R cross P, pretty much we're always going to find angular momentum to not be 0. And we might find it constant, though, and that's what we're going to look at right now. And we're actually going to be finding the angular momentum with respect to two different points, M and N. And that's why those are marked here. I'm going to find the angular momentum with my origin at point M and the angular momentum with my origin at point N. Now, you'll notice that both of those points are along the axis of rotation. Right, so they're valid in the sense that they are along an axis of rotation here. But we're going to compare them, do a similar analysis to what we've just done, which is, number one, find the angular acceleration for each, and then take the time derivative of them. Are they changing in time? And then compare that to the sum of torque with the same origin, one at m and one at n. Right? So because the sum of torques should equal the time derivative of angular momentum, that means that the time derivative of the angular momentum we find should equal to the sum of torques if we find that manually. And it also means that the derivative of angular momentum with the origin at n should equal the sum of torques with the origin at n. Okay, so this is going to be a little bit longish, so just get ready for this. We're going to do a lot of cross products and go through a lot of things here, but I think it's interesting. We're going to start with actually the easier case where I'm going to place my origin at m. And we're going to focus on finding then the angular momentum at m. So with my origin at m, all right, so with my origin at m, let me mark it right here on this picture below. My r vector will then point from m to the location of the point mass. So this is r sub m currently. This is going to differ from when I look at r sub n, when I have n as my origin, right? Because when I have n as my origin, my position vector will look like this, right? It's a little bit different. But here is r sub m. And so what I'm going to be doing is writing out a vector for r sub m. And I'm going to be crossing that with the momentum vector, m times v. Now, the momentum vector is the same for everything. And if I look down here with the top view, I see that that momentum vector is just m times v vector, m times v vector, and it's actually pointing tangentially. So right now, even though you can't see it, remember we talked about the fact that the velocity vector is pointing out of the board. So right now, m times v, which is the linear momentum, is pointing out of the board. And in fact, it always points tangentially, like I said. And I should write that v is just the magnitude v in the theta hat direction. It points tangentially. So let me go back up here. Sorry. And just kind of denote that, remember, this is the radial and this is the theta hat direction. And remember, it moves around with the particle that's moving. But I can map it to the xz plane, right? Because remember, this is x and that's z out of the board, no problem. Okay, you'll notice also that my r vector, it points radially. And another reason I know that is because here is the r vector sub m at the top with respect to the point particle here. Well, here it is when it's on the other side. And, if the particle was here, or here, or here, this is what the r sub m would look like. It points in the radial direction at all times. So I can actually write my r sub m as just having a radial component, r hat, and the magnitude of it is just this radius, L sine theta. That's it. Now, just as a side note, I know this V. I can plug it in anytime I want to. I just don't want to yet. And what I'm going to do here is ultimately just prove to you guys that r hat crossed with theta hat, oops, is going to equal to the positive y hat direction. I know this seems a little crazy, but you can see how we're leading that way, because for the angular momentum vector, L sub m, it's going to be equal to L sine theta in the r hat direction crossed with V in the theta hat direction. And so, these are exactly perpendicular to each other. Here in this picture above, this is r sub m, and this is V, or mv, the momentum. At every single point, here is m times v again, here is r. In the circle, they're always going to be perpendicular with respect to each other, r cross mv, r cross mv. They're always perpendicular to each other, and so I know that I can write this as really just going to be L sine theta times v times r hat crossed with theta hat. And so eventually I'm going to find this to be VL sine theta in the y hat. So let me just prove to you that r hat crossed with theta hat is in the y hat direction. You can also use the right hand rule. Line your pinky up with an r hat vector in such a way it crosses into the v, and your thumb should be pointing out of the board. And since this is the zx plane, out of the board is the positive y hat, because we were looking at the top view. But let's just show it. I'm going to be doing that by looking at this circle, so I'll go to the next page. Redraw that circle. This is the top view. And we're saying that this is the z hat, and this is the x hat direction. And I'm just going to choose a point here. To describe my particle. And if so, here's its position vector, and this would be the r hat direction, and this would be the theta hat direction. And I'm going to go ahead and call this angle phi. And just so that I can understand it, I'm going to rewrite r hat in terms of sine phis and cosine phis. So here's my r hat vector. I'm going to represent it by a positive x hat and a positive z hat component. In fact, if this is r hat, it's going to be made up of this positive x hat and this positive z hat component, and this angle will be phi right here. So r hat, in fact, can be sine of phi z hat plus cosine of phi x hat. And then here is theta hat, the tangential direction. The tangential direction here is perpendicular to r hat, of course. And this angle is phi. Let me look at it here. I want to find this angle because that's the one I understand. That means this is 90 minus phi, phi, 90 minus phi. That means phi is up here. And that means that I can break this up into a component in what is the positive x hat direction, but is the negative z hat direction. So in the negative z hat direction, I have minus cosine phi z hat, and in the x hat, I have positive sine phi. And so now what I'm going to look at is r hat crossed with theta hat, and I'm going to do that by looking at the determinant in the x, y, z plane, where I've been consistent with the common notation. I'm just going to write first vector r hat, component by component, It has a cosine phi in the x, a 0 in the y, and a sine of phi in the z. It has a sine for the theta hat direction, second vector. It has a sine of phi in the x, 0 in the y, and a minus cosine phi in the z. And looking at that determinant, there'll be 0 in the x, there'll be something in the y, and 0 in the z hat. So the complete determinant is minus y hat minus cosine squared of phi minus sine squared of phi, which of course is minus 1, or this whole thing is positive y hat. So I've just really proven something that you could have done by the right-hand rule, if I could explain that to you well, that r hat crossed with theta is always positive y hat. So kind of going back to what I have here for the angular momentum vector, I'm just really proving that this is always in the positive y hat. And the angular momentum vector at point M, is going to look like this, L sub M. As it moves its way around the circle, it's always going to be looking like, in fact, it's constant. V is constant, L is constant, theta is constant, and the y hat is constant. L sub M, which I've really found here now, is just this constant thing that moves around as this thing moves in a circle. It's just going to be moving around like that in the circle. Always constant, always pointing upward. That's what the angular momentum vector looks like. It doesn't change in time because, again, V is a constant. And I do have the luxury now of plugging V in here. Oops. So here was my angular momentum vector. If I plug in V, it's going to be the square root of GL sine theta tangent theta, all of that times L sine theta, and the y hat. Everything is constant here. And so if I take the first time derivative of this vector, it's 0, because nothing changes with time because theta was constant. And so that's L sub M, that's the time derivative of it. And what I'm going to do is to check now, does the sum of torques equals to 0 if I choose the same axis that I had before for M. So let me go ahead and take a look at that really quickly. Let me copy this again. Erase some of this, because now I really want to look at a force body diagram to do torques. So I'm going to keep the same axes, M, right, to be consistent, and I'm going to find the sum of torques now at M and say, does it equal to 0? So I'm going to quickly do my force body diagram again. I know I did it earlier, but not on the page. So here's my tension force and here's gravity. That's really it. My R sub M is the same as what it was before. Here's my R sub M, right? If torque is equal to R cross F, R is going to be the same for all of the point particles. So, for all of the forces. So my R is going to be the same for this point particle. I'll have R cross T and R cross mg, and I can see that they're both going to be contributing something. They both have a perpendicular component. So let me right away break up this tension vector. And if you remember, I had T cosine theta here. And then I have this T sine theta over here. And so if I want to think about torques the way that I do, as the magnitude being R times F perpendicular, well, here's my R. For tension, my F perpendicular would be T cosine theta. And this would cause a rotation, right? R cross T cosine theta would cause a rotation this way, so I know that the direction of this thing would be creating a clockwise direction for the most part. Now, this isn't exactly because here the clockwise direction is associated with into the board, which is the minus z hat direction at this point, but it's actually associated with the minus theta hat direction, right? Because this thing is moving in a circle. So the torque from tension is R, which is L sine theta, times the perpendicular component of the force, times what looks like the minus z hat direction, which is really the minus theta hat direction in this case. If you want to think about it as minus z hat for right now, it's fine. I'm just going to prove to you, honestly, that the torque from tension and the torque from gravity cancel, because those are my only forces. So the torque from gravity will also be L sine theta, right? That's just my R value, which is still the same for gravity. And then gravity, of course, is 100% perpendicular. So my F perpendicular, right, to my R vector for gravity is just mg. And then the direction of this, well, this would be causing a rotation counterclockwise. So that's normally associated with sticking out of the board or the positive z hat direction. But here that's the positive theta hat direction. So positive theta hat direction. So you can see right away that there's going to be cancellation. Again, you can think about this as positive z hat if you need to right now. You can see there's going to be cancellation. And in fact, they'll exactly cancel if mg equals to t cosine theta. And they do, because the sum of forces in the y equals to 0 for this problem. So if we scroll back a page, we use that to solve this problem. And so these are the two torques acting on the system. If I sum them up, they're going to add up to be 0. So yes, that does jive with the change in angular momentum being 0 in this case. Okay, so let's keep going. And let's work a problem, or work it now here at the top with my origin at n. So let me go ahead and cut this out one more time. Right. And remember, what I'm doing is instead of my origin being at m, my origin is now going to be here at n. And I'm going to rework this entire problem now with an origin at n. And I'm going to find the angular momentum vector at n. And then I'm going to go ahead and take the time derivative. And I'm going to compare it to the sum of torques where my origin is at n. Just to get an understanding of the angular momentum of a point mass. Fortunately, this one moves in a circle. Okay. Right, so just don't want to forget that it's coming out of the board here. Okay, so one main difference between before is that now my R vector has changed, right? So when I write L sub n equals to R cross mv, really the only thing that changes with my choice of origin is the R vector. And here it is. This is going to be my R sub n. Now, clearly, I can write that as an addition of this vector plus this vector. And you should note that this is just R sub m that I had before, right? This is the same position vector that I had when my origin was at m. So just looking at R sub n and writing it out to get ready for solving this problem, my R sub n can be written as R sub m plus this component, which is actually going to be in the minus y hat direction because this is positive y hat via the problem. And this is going to be, since this magnitude is L, this is just going to be L cosine theta. So plus L cosine theta in the minus y hat direction. I don't really feel the need to write this out again. I have it written out before. It's just L sine theta in the radial direction, right? L sine theta radial. This one is just pointing always in the y hat. So the extra component changes like that. And so when I plug this into my cross product, L sub n is equal to R sub m plus L, well, minus L cosine theta y hat crossed with m times the velocity vector. Remember, the velocity vector point is v in the theta hat direction. What I'm going to get are really two cross products out of this, R sub m crossed with m v theta hat minus L cosine theta y hat crossed with m v theta hat. And this is just L sub m. Crazy, right? So L sub n is going to have a component that is just the angular momentum when I had my axes here, because that's R sub m, minus L cosine theta, and I'm just going to pull that mv out, y hat crossed with theta hat. Now, the interesting thing is that we know that this is a constant, right? We've already shown that it points in the positive y hat direction, its magnitude is a constant, so when you take a time derivative of this, it's just 0. You know, this is not a constant. Y hat crossed with theta hat, well, you're going to see that y hat with theta hat is going to give you kind of a y hat crossed, I'm doing it right now, y hat crossed with theta hat is going to give you kind of a minus radial direction. So this thing is going to have a minus radial component, and positive that it's going to actually give you a radial component which changes in time. Remember, theta hats and r hats, they change in time as you move around the circle. So like right now, theta hat is pointing out of the board, but later on over here on the other side, remember, it points into the board, so it changes its direction, and so does the radial component as it moves around. So this one's going to be related to the r hat vector. Let's take a look, and to do that, I'm going to go back and get my theta hat that I had here on my r hat. I had them written out in the xz plane. Paste them over here to remind me, because now I really want to look at this y hat crossed with theta hat vector. And so I'm going to look at y hat crossed with theta hat via the cross product, where everything is x, y, z. So y hat with theta hat means that y hat has a magnitude of 1, and it's 0 everywhere else. And theta hat, remember, was sine of phi in the x hat, 0 in the y, and minus cosine phi in the z hat. And this does not look like a 1. Let me draw that again. 1. And so taking the cross product, there's going to be an x hat, no y hat, and there's going to be a z hat. So for the x hat, it's going to be minus cosine of phi. And for the z hat, it's going to be minus sine of phi. And so this is going to be equal to minus cosine phi x hat minus sine of phi z hat. And if you look up above, you'll see that this is just minus the r hat direction, minus the radial direction. So y hat crossed with theta hat is minus the radial direction in this case. And so the full angular momentum vector with the origin at point M will just be the angular momentum vector at M plus L cosine theta M times V in the positive radial direction after those minus signs cancel out. And so what that looks like, if you don't mind me erasing this, is the angular momentum is going to have a component in the positive y, like before, but also in the radial, right? So it's L sub m, and then it also has this kind of radial component, right? And then L sub m. And those will add up together to look like this. So this is L sub n. And as you make your way around the circle, L sub n is always going to have a radial component. So if this is my circle that the mass is tracing out, right? What's actually going to happen, it has this little kind of precession, right? It has this little kind of precession, traces out this little circle up above here too, with its little radial component. So if you put your thumb in the direction of that angular momentum vector, it's kind of tracing out its own different size circle right there. Kind of tracing out a cone too. And I thought that was interesting. But it changes in time. I can see it because its direction is changing in time as it moves around the circle, right? It has this radial component in addition to this constant L sub m. So I guess I should write out what L sub m was before. VL sine theta. VL sine theta in the y hat. Remember, it was just constant. So this constant term is in here, but this non-constant term that changes with the r hat is in here too. So even though the magnitude is constant, r hat changes as a function of time. In fact, we'll be taking a derivative of the r hat vector in just a second and understanding that phi changes as time as we move around the circle. So here's how I defined phi. And when I move around the circle, of course, phi is changing as a function of time. So just prepping this so we can think about taking the time derivative of L sub n, which will effectively be the time derivative of L sub m plus the time derivative of L cosine theta mv in the r hat direction. We already know that this term is 0. We saw it before, so we're just concerned with this one. And I've argued that really it's only the r hat direction that changes in time. This is why when we integrate and take derivatives of it, we have to be careful. And how it changes in time, I'm going to kind of treat up over here, just by taking a derivative of this thing component by component. So derivative of sine phi will be cosine phi times d phi d theta, dt, so on and so forth. So d dt of r hat will be cosine of phi d phi dt z hat. Derivative of cosine of phi will be minus sine of phi d phi dt x hat. Remembering that d phi dt is just omega, the time derivative of r is equal to omega times minus theta hat direction. So here's theta hat. Well, in here is a minus theta hat. So the time derivative gives us a minus omega and a theta hat direction. So fun and games, right? What does this even mean? Well, not much, but first we're going to compare it to the sum of torques, and then we'll be like, ah, yes, this does agree with the net torque acting on the system. I'm going to have to play around with this afterwards, but let's look at the net torque, where N is my origin. So again, I'm going to go ahead and copy this. And we're going to work at finding the net torque on the system with respect to our axis here at N. So what is the net torque at N? Well, first I'll be looking at my R vector. My R vector is going to be R sub N for every single force acting on this system, right? Because torque is R cross F. Well, for a point particle, all of the forces act at the same point because there's nowhere else for it to act. And I'll have gravity, and then I'll have the force of tension. All of them have the same R sub N, so the torque from tension, the torque from gravity will be R sub N across the tension force. This will be R sub N crossed minus mg y hat. This one is 0 right away. Look, R and tension are anti-parallel to each other. There are no perpendicular components, so the torque is 0. Looking at the torque from gravity, I can see that there is going to be a component of gravity that's perpendicular. But, you know, I already have the full R sub N vector written out, don't I? Where are you? Yep. I already have R sub N written out, so let's take a look at it. It's R sub M minus L cosine theta in the y hat. And remember, R sub M was just L sine theta in the radial direction. So I feel like we should take the cross product again. You guys are like, really? I'm like, yeah. So we're going to look at R sub N crossed with gravity to find out what is the torque from gravity. So L sine theta R hat minus L cosine theta Y hat crossed with minus mg Y hat will equal to L sine theta R hat crossed with minus mg Y hat plus minus L cosine theta Y hat crossed with minus mg Y hat. These two vectors are parallel, so this whole thing is going to be 0. And really, I'm crossing the R hat with the Y hat. Let me get my little identities out here, because I'm going to look at this stuff again. Oops. Oh, I guess it gave me the whole thing. That sucks. Oh well. All right, sorry, technical difficulties, guys. I'll get it together. Watch. Okay, so this cross product is going to give me L sine theta minus mg times R hat crossed with Y hat. So let me get my R hat out here. X, Y, and Z. R hat crossed with Y hat. Did we do that one already? No, I don't think so. No. Doing it. That's going to be... This is an X hat. Cosine phi 0, sine phi, and y hat, magnitude of 1 there. I'm just looking at this. I already know that r hat crossed with y hat, oops, r hat crossed with y hat is going to be something like the minus theta hat direction. I'm using the right-hand rule that I was trying to explain you guys to understand that. But let's just take a look. Taking the cross product, the x hat will have a term, the y hat will have no terms, and the z hat will have a term. And at the end, I'll have x hat minus sine phi plus z hat cosine of phi. And if you look at that, that really is just equal to the minus theta hat direction. And so the cross product, or the torque from mg, will be minus mgl sine theta times the minus theta hat direction. Or mgl sine theta, theta hat. You know, and that's going to be the net torque acting on my system. It's just going to be the torque from gravity. And I'm going to say, does that compare to what I found here? Oops. Did I lose a minus sign somewhere? I did over here. Sorry, this should be positive here. I'm so sorry. This is minus and a minus, right? Oh, no. Crap, I lost a minus sign somewhere. Okay, but here, I won't alter it. I have lost a minus sign somewhere. I'm going to go back and find it. I just don't know where. But this was my time derivative. Just let me show you. This is my time derivative of dl dt at n. They don't look like they compare right now, but let me plug in that v is the square root of gl tangent theta sine theta. And let me also plug in that v is, or omega is v over r. Here, r was L sine theta, is the radius. It's how far away I am from the axis of rotation for that point mass. So actually, when I replace this with omega with v over r, I'm going to get minus v squared cosine of theta over sine theta. The L will disappear times m theta hat. And when I plug in v squared, I'll get minus gl tangent theta sine of theta. This is cotangent of theta, m cotangent of theta. And cotangent of theta times sine tangent of theta is 1. And you can see that these are the same up to this minus sign that I've lost somewhere. So, excuse me. I don't know where it is, but do you see that these are the same? MGL sine theta, MGL sine theta, up to this minus sign. So let me just go back and find that for you guys really quickly, and then we'll call it quits. But ultimately what I'm doing here is I'm just comparing the sum of torques to the time derivative of the angular momentum vector. Where did I lose a minus sign? Was it here? minus that L cosine theta y hat minus L cosine theta. This is y hat with theta hat minus r hat. Gives me a positive r hat. And then the time derivative of r hat. Gosh, you guys, I can't find it. Cosine, d phi dt, sine. Gosh, I lost a minus sign somewhere, you guys. I think it's in here. Ugh. Minus signs, minus signs. Can't find it. Okay, guys, I'll look for it later. I don't mean to. Maybe I'll append to this in just a second. So we've actually been going for an hour and 20 minutes. So this is going to be the complete lecture for our Tuesday lecture, the last week before finals. Okay, so I'll probably append to this when I find the minus sign problem. All right, adios. Talk to you later with more angular momentum. Bye. Hi, guys. So I'm back really quickly. I found my error. It wasn't actually a algebra error, believe it or not. It had to do with this omega. Where are you, omega? Here. It turns out I treated this just as a magnitude, but in fact, d phi dt was changing in a negative way. So this should have actually been written as minus absolute value of omega, and you can see that. If you go over here and you think about as this thing moves around in a circle this way, phi is changing negatively. So, you know, I probably shouldn't have defined this. You know, honestly, I think I just kind of switched up what I called the positive theta hat direction a little bit here because everything was upside down. Anyhow, because of that, which is fine, honestly, but because of that, this direction as it moves around in a circle this way tangentially, phi is actually getting smaller, so d phi dt is changing negatively. So that's where that was. Looked everywhere for that minus sign. I'm like, where is it? And there it is. This should have been minus absolute value of omega for me to use this. Okay, hope that helps. After this video, I'm going to post a quick video about the right-hand rule just to clarify what I was trying to show you earlier. Sorry about that. It's funny though. Bye. Hey guys. Just a quick video to show you my hand. This is my right hand. And I wanted to show you the right-hand rule that just gives you the direction of a cross product, R cross F. So what I want you guys to do is to align the pinky with the first vector R, and you can see that there's infinite ways to line up a pinky with this one vector. But I want you to line it up in such a way that you can cross or fold your hand into the direction of the next vector, F. And then your thumb points the direction of the resultant vector. So R with pinky so that I can cross it into F, and thumb points the way of the resultant vector out of the board. Okay, hope that helps.